Starting. So the next part is problems with data sets. So you probably have your own data sets, which maybe not are so large. And first thing is imbalance. That is something that you can have quite some problems with. You may have too few examples. The samples may be too homogeneous. And of course, there are other problems with the data related to noise, sharpness, etc. And this also gives you some headache probably when you start building analysis algorithms on top of them. And one thing is that can happen based on these problems is bias, that if you have too few examples of one type, then you can come into that things are misclassified. In some cases, it's maybe not so bad depending on the task, but in this case, a guy got very upset that his friends were classified as gorillas, which is understandable. That is probably because they had based the training on some database with a lot of monkeys, apes, gorillas, and maybe not so many black people. And that then resulted in this massive misclassification. The solution Google came up with was just plain and simple. Gorillas doesn't exist in the classification database. And with that, they actually solved the problem. It's maybe not the nicest way of solving it. And the other way is to add more categories, more diversity in the data. So for example, here we have some faces of celebrities with a lot, only the faces. And this is even categorized even further. So you have categories like eyeglasses, bangs, pointy nose, and so on. So you have different hairstyles, you have different things on the face, you have different face shapes, maybe also mood, like smiling, and all that is even added to this database. Skin color doesn't show up, but I could imagine that is also in this data set. So for each picture, there is a large table of many different categories. And these categories may be repeated between different people, but that doesn't matter. But it gives you categorizations and making it easier to classify different people and ways they look. Then we can look at this example again with Mnist numbers. Now I'm reducing myself to only looking at 1, 2, and 3. And you can see here in the digit distribution, this histogram, that we have more 1s than 3s and 2s. And this is what we are going now to play with in this testing and see what happens. The other thing is also with limited data, that is really a big problem for many methods, that you have too little data to do any decent training. And there are different types of that. In one, the basic thing is that you have too few data points or too few images to describe what you want. Another thing is the problem of unbalanced data, that you have two classes in your data. And these classes are very differently represented in the whole data set. And if you look at this one here, you have a little tiny bump that is class 1. And then you have all the other cases from where you want to identify this anomaly. This is an easy case. Identifying this is just saying that all values above this point belong to this tiny class. More tricky, however, is if you have them overlapping in this way. And with this noise level, you can see that what we want to look at only appears as a small deviation on the larger category. That is much harder to detect, and you may have to use different methods in order to handle this. And it can be that you have maybe 1%, 1 per mil, or even less representations of this underrepresented data type. Then you can also have little or missing training data. So you have, in principle, you have a lot of data. For example, in case of in a project I worked on, we had tomographies of soil with the root system in them. And such tomographies, there are plenty, but it's very hard to mark up and annotate the roots. And that's why we don't have much training data for the segmentation algorithms. With that, we needed to take some different approaches to come around that problem. And one approach is actually working with augmentation. And that is when you have too little data which is marked up and you don't have the resources to provide more data. So we can, you don't know really, on one side you may not be able to measure more, or you don't have time to mark it up, and so on. And also in medicine, it's also a problem because sometimes a disease only happens very rarely per year in one hospital, and you're not able to identify it or collecting the data you need. And also then you have all the ethical issues of anonymizing data, etc. So in medicine, it's a tricky thing to collect data and making it available. So what we can do is to do this augmentation, which means we transform and adjust or modify the images in different ways. So one thing is adding a lot of different geometric transformation, like moving it around, zooming it, rotating it, changing the intensity by normalization, or scale it, or adding biases, etc. Can also play with different colors or even shear the whole image. On top of this transformation, we can also add noise to the data, and also smoothness, so blur the images. So that would be just applying some kind of convolution on the data and with different kernels, and then it would also provide you different augmentations. Here you can see some images of that. In this case, it's pictures of retina blood vessels. And we have up in the corner, we have the original image, where you can see the blood vessels, just a black background. Then you can do elastic deformation. You can see that the grid has been a little shaky. You can also rotate it, you can zoom it. And then you have the mask, which you have to apply exactly the same category, same modifications. But there are also limitations, what we can do. So these modifications, they are kind of imposed by the type of data we have. For example, CT images cannot get flipped. They cannot be, the head is always in the same direction, left, right. Well, that should also be maybe looked out for. And also the values in the CT images, they have a physical meaning. So it's a Hounsfield unit, which scales with the attenuation coefficient. And changing them too much, then you would actually go out into something that is not really physically possible with that modality. So that's not what you can do. And then, of course, you cannot distort too much, because you will still want to recognize the features in the image. And that shouldn't be, if you modify them beyond recognition, you can't tell anymore that it is like some bird or a dog, but it's something. So there you have to be careful about how much you distort. One tool that you can use for this, here you see the manual for, or the manual page for something called the image data generator. It's a function in the Keras module, and that helps you to create new data sets based on what you already have. And one example is here. We set it up where we have different parameters that we are playing with. So we can rotate within plus minus 30 degrees. We can do some width shift percentage, some shear range, some zoom range. If we rotate, there will be some kind of gaps and they need to be filled out. Could also possibly do some horizontal vertical flipping, but this is deactivated right here. And let's go on. So let's play with augmentation on the Mnist data. So here I have, on this row, I have the original data. And then we have also augmented it in different ways. You can see here the one is rotating wildly. Here it's even scaled and rotated. And this little piece of code here produces this example. So most of it is actually about the plotting, but the part up here is doing the augmentation for you. Another data set we can play with is the Cfar10 dataset, which is not only having people, but it has also different machines, animals. So you can see here the categories, and here you can see variations of that. And you can see it's a pretty large variation in what it is. Cfar is based on very small images. I think it's 32 by 32 pixels. And but there are many, many in it. So that's something we can also work with. So let's load it. We have it in the module Keras datasets. So here we can just say Cfar10 load data, and then you get the images and the labels. And then we set up the what you can do, which kind of transformations. And here we are even more less restrictive, so we can even flip it in different directions. And now when we run the augmentation, you can see that in some cases, the distortion doesn't really make sense. I mean, this doesn't look like a horse anymore. And that's then less useful. So you have to actually see, check if the augmentation makes sense before you actually use it in your training, because otherwise you may end up in very misleading results in the output afterwards. So now let's leave the data sets and go into baselines. And that's baseline is already some kind of algorithm that we are going to use to verify how to work with the data. So it's in principle, it's a very simple, very easy to implement model, which illustrates what you want to show. And it also should serve as a kind of worst case scenario when for a model that learns nothing. If your model is doing worse than this one, then it's really bad. And it's definitely useless because it can be really giving you misleading results. So why do we need it? Just to show here, the example here is we have this baseline algorithm model that more than 99%, that is more than 99% accurate in predicting breast cancer. And the algorithm looks like this. Do I have breast cancer? And you provide the information, age, weight, and race. And the algorithm tells you no. That's it. This is very good because because breast cancer incidence is 89 out of 100,000, which means 0.09% cases, which means if we say no, we are actually accurate to 99.91%. Fantastic, or not? No, not really. Then we actually don't even target what we are after. So you really have to have something a little bit smarter. In scikit-learn, there is a dummy classifier which can help us as baseline, and this one has different categories. In this case, strategies. Sorry. In this case, we are talking about the most frequent as classification. So if we have here the three numbers 0, 1, 2, 3 are some kind of measurements, lab results, whatever. And these are associated with healthy, and cancer. And when we execute this, it says we have this classifier, which is most frequent. And looking at what it gives us, we try it now for the three cases. We have input value 0, 1, 3, and 100. And the output, when we use this to predict something, is that prediction for 0 is healthy. Prediction for 1 is healthy. For 3 is also healthy. But you can see here that it's actually should have cancer. But it still gives us that it's healthy. It's about almost the same as the previous example where we had the cancer prediction, just saying you don't have it. And then if we put 100 here, it also says it's healthy, which is probably not very likely. The reason is that this classifier is working with the most frequent. So healthy is most frequent. And that is our prediction in this case. So let's try out the dummy classifier on the Mnist data. And here I have 24 digits and their labels. And you can also see here the histogram, how frequent all these digits are. Now what happens if we run this through the dummy classifier? So let's try the classifier first. And we do it with the dummy classifier most frequent. We fit all our images together with the labels. And the basic test tells us ones. Everything, all images are ones. So the question is now, we don't see what actually these images show us. So maybe we should take a closer look to that. And here we can see that it's clearly not ones in all these pictures. And also the associated label tells us differently, but it predicts a 1, a 1, a 1, a 1. No, this one actually is a 1. So this one does right in 4, 5 cases. Otherwise, it does wrong. So it's not really a good choice of prediction algorithm. But it's anyway some kind of baseline. The reason for this is that we have here that the ones, they are the most frequent one, and that is what then gives us the response for all data. So yeah, we could really use something better. And the better one would be to use an algorithm called nearest neighbor. It is a popular machine learning method, and actually it's also called K nearest neighbor. And the principle here is that if you have a point, say this one, no, sorry, that was wrong. Yeah, okay. If you have a point somewhere around here, it looks for, the algorithm is looking for the point in the training data which is closest. So that would be that one. And that is what it will assign as class for the data. If you add number of classes, then the K here, then you say you have to compare it to, say, if you have four nearest neighbor, then it would look for all these 4 neighbors, and from that it takes the majority mostly and tells that this is really the one that is the class. If you are close here, then it can be difficult, but this decision line here tells us where the boundary goes between the 2 classes. This sounds clearly a bit better than the majority voting. So let's try and see what we get out of that. Again, we load the data with the numbers, and then we train our K nearest neighbor. We get that from the scikit-learn module. There is one called neighbors here. Oops, that was a bit slidey. Then we say we would want to create a neighborhood classifier with only one neighbor. And then we do the fitting. We have our images, and here they are reshaped. So actually what you're doing is reshaping the images with some number into it into a very long vector where you have only 0, 1, 0, 0, 1, etc. So this is what's happening here. And when you use the k-means classifier, it will compute the Euclidean distance to these vectors. And then it gives us the outcome from that. And let's try. We fitted it, and let's see what comes out. We have here some images coming in, and we get the numbers 5, 0, 4, and so on. And let's look at what that looks like. And we see, wow, we actually predicted everything perfectly right. That's not really true, is it? No. A baseline of this kind shouldn't be able to classify 100% correct. What we did was a very common mistake, that we used the same data that we trained with to test it. And that means if we have, so let's just draw some decision space. We had our different points in some decision space here. This is our training data. So these belong to the 6, these belong to the 1, for example. When we use the same data that we trained with, then if we send in a 1 image, then it's actually this 1 image or that 1 image. And of course, you will predict very precisely exactly the same as you trained with. So how to get around this problem is, no, wait, that was, okay. Now I got a little bit on the wrong place, sorry. Let's see, somehow something got lost here. Yeah, okay, let's start from here and go into display again. So that was that one and that one and that one. So what we need to do now is to run the whole classification based on a different part of the data set. So now instead we are going to get numbers outside of the points. So sometimes these no. Oh, it doesn't react now. Okay, sometimes we get numbers outside of the train data, and this gives a little bit more uncertainty. And you can see here now that we actually sometimes predicted a 2 into a 3, a 4 into a 1. Here we did it right. And there we got some pretty good ones here. And then all of a sudden there is a bad one again. And this gives us a more realistic result. And a way to quantify how good these results are is to use something called the confusion matrix, where we have different things. This is strange. Okay. We have in this on these rows, we have the actual true. That is what we know it should be. And the other one in the columns here, we have what the algorithm predicted. So if we have something along the diagonal, we are good, because that is exactly predicting what we wanted to predict. But we can also get some numbers out on the sides here. We would expect it to be a false, but we got the true. And here we expected a true. So I got the question here about how the nearest neighbor is used in the number classification. Yeah. Now I really need to have my annotation on. So, okay, I need to do. So let's go back to the question about the nearest neighbor. So the images, you saw before you had an image of, for example, a 6. It is made of, I don't know, maybe 8 by 8 pixels. This is formed into a vector with ones and zeros, pretty many. This one is actually 1 by 64. And when they come in a new image, say we get a 2, that's also reshaped into this kind of vector. And what you do in the algorithm, this probably has some different constellation, yeah, whatever. What you do is you take those two vectors and compute the Euclidean distance between them, which is done as, let's say we have A and B. So this is the inner product of A and B. So we would actually compute A times BT. And that gives us some number, whatever, let's say 2.5, whatever. And this is now compared to the training data. So the A is the training data. And in your training data, you have now a lot of points. And these points are compared to what is incoming. And then you get different numbers. So one maybe gives 2.5, the other one gives 1.1, the next one gives 0.5. And in the end, we take the one that has the shortest distance according to this calculation and assign that the class. Does that help you? I hope so. Yeah, good, great, thanks. That was a little sidetrack. Anyway, from this confusion matrix, you can also see if there is an unbalance in what is done right or wrong. Sometimes you have no zeros, no So you have maybe a 0 here and you have 50 here instead. That gives you a really skewed view that you actually mispredict falses a lot, while you never mispredict the truth. So you can see here where towards which direction your method is biasing. And let's go on to, okay. So, oh, I need to clean this. So let's go on now to the Mnist classification example. And here you can see again, you have this a diagonal, which actually does a pretty good job. It's pretty good. Okay, it says here we have an accuracy of 56.9%. And there are some cases which are very critical. And one is here, that you should have the true label 3, no, true label 4. And there are even more that are classified as a 9. And if you look at the 4 and the 9, if you rewrite the 4, you could look something like this. And then you can see that there is quite a resemblance between them. And that is actually confusing the algorithm when it tries to classify. There are other cases, for example, the 1, for some reason, is very often predicted. So there is a long tail of mispredictions. So it's very often that it happens that it tells us that we have a 1 in the data set. The reason for that, I would guess, is that the 1s are overrepresented in the data, and that's why also you have more points. And a way to get around this problem is to actually add more classes. No, add more neighbors. So if we go back here in, okay, if we go back now to our training, so we set our training to work on, where is it now? Here. We set our nearest neighbor classifier to train only on one single neighbor. So if we increase that to 3 maybe, and then we do the fitting, takes a little while. Okay, I need to load the data. Let's see where we got it here. So, and then we run it. And now we don't have to do the obvious case, but we go straight on to this case and see what happens. Yeah, not better actually. That's disappointing, but let's see what happens to our confusion matrix now. It needs to be calculated. Oh, I need to do some more stuff. Okay, that's it. And well, it wasn't particularly good. It even got worse on the 1s. So it really shows us that there are plenty more 1s than there are other numbers within the data. So this is probably looks like we have a very skewed data set here, and that's not good for the purpose of the training. And another thing I can tell also is that we have very few data sets to play with in the training. So maybe we should change how we train this algorithm. Let's see, we had it here. So we did only 24 images, and right now I actually don't know how many I really have. Let's check. So apparently we have 60,000 images and we only train with 24. So if we increase here to work with 200 images instead in the fitting. No? Oh, sorry. Then we need 200 here and 200 here. So now we did that training, and let's see what comes out now. Yes, now we got a lot better. So you can see how important it is to have the correct size of the data in order to get a good classification. This was a little bit a side track, actually. I think we are going to talk more about k-nearest neighbors in later lectures. But anyway, here you can see the demonstration about the importance of having first sufficient data points in the training to give the good experience of our model. And second, also maybe work with more neighbors to get a more robust response. And now looking at this, let's see. Yeah, that's okay. And let's see what comes out from this test. Now I'm actually cheating a little bit because I have some overlap with the training data. Now we got slightly, quite much better results. So now it actually gets the 4 much better than the 9 as we had it before. Probably if we train it with 1,000 cases or even 2,000 cases, we would get even better results. And you can also see here, we had, I think it was 57%, and now we have increased accuracy to 70%, only by increasing our data set and also increasing the number of neighbors in the configuration. Okay, so this brings us actually to the end of today's lecture. And as a small summary, we have been talking about how important it is to have good data and also what we mean by having good data. Data preparation is certainly an important thing. And therefore, we have to prepare our experiment data in a correct way in order to give the precise results we want afterwards. If we don't have sufficient data, there are ways to get around it. One is to use augmentation, and the other one is actually to borrow other people's data sets, and with that come closer. Then the last part was about baseline algorithms, something that is very useful if you try to compare the performance of what you are doing. What I didn't say was that the baseline could also be someone else's algorithm. So if you read a paper and you're not really happy about the performance they provide, you can use theirs also to make your point that this algorithm does this and that good, and my algorithm is so fantastic, it does it twice as good, or whatever. And that is also the idea of having these baselines. But you can also do it in a way that you have 2 baselines. It could be the, say, dummy baseline, which does the basic task more or less, but not much more. Then you can have the other people's algorithm also as a baseline, and then you come with your alternatives on top of that. So the full evaluation can contain several different baselines. And that was all for today. And afterwards, in the exercises, we have again created these breakout rooms. So if you have questions or things to discuss, please join Stefano and me in these breakout rooms. So thank you for today.